Chapter 6, Section 2 is called partial derivatives. Partial derivatives, page 562, exercise 4. Z is a function of x and y. Z equals 2x to the third plus 3xy minus x. There are 4 things in the directions to find. This symbol, this is a different kind of D, like Greek letter. It's actually lowercase delta. Delta Z over delta X. This is not the same as the derivative, but it is called the partial derivative of Z. When down here we say with respect to X, that means with respect to X means pretend any other variable is a constant. You get to pretend. So I see an X in the denominator. So we say the partial derivative of Z with respect to X. So any Y we come across, we're going to treat it as if it was a constant. So in my mind, I would rewrite this as 2x to the third plus 3y times x. I just switch the order, minus x. So differentiating with respect to x. For the first term, we get 6x squared. The second term, 3yx, that in my mind, in partial derivative land, is a constant times x. 3y is a constant for this moment. The derivative of a constant times x is the constant. Just like the derivative of 7x is 7. And this last term, the derivative of negative 1x is negative 1. That's it. That's called the partial derivative of z with respect to x. And the partial derivative of z with respect to y means, this means pretend that x is a constant. So going back up here, the first term is 2x cubed. To me, that's a constant because 2 is a constant, x is a constant, 3 is a constant. The derivative of a constant is 0. The next term is 3xy. We're pretending x is a constant. The derivative of 3x times y is just 3x. The derivative of a constant times y is the constant. And negative x is a constant, making the derivative 0. So we say the partial derivative of z with respect to y, so I actually have the wrong symbol here. These are not supposed to be regular d's. Is this up here is 3x. So we're still on exercise 4. Z equals 2x cubed plus 3xy minus x. It says find the partial derivative of z with respect to x at the point negative 2, negative 3. That means we have to take the answer we got back here, 6x squared plus 3y minus 1. And to find the partial derivative of z with respect to x at this point, we use this. It's 6 times x squared plus 3 times y minus 1. For x and y, we're just using these numbers. And that comes out to be 14. In the last part of this exercise, it says find the partial derivative of z with respect to y at the point 0, -5. To get this answer, we have to use what we got here. The partial derivative of z with respect to y is 3x. So here it's 3x, means 3 times this number. So the answer is 0. Okay, number 8. F is a function of x and y. It's equal to x squared minus y squared raised to the 1/2. It's actually written in the textbook as the square root of x squared minus y squared. In the directions it says find f with an x subscript. That's another symbol for the partial derivative of y. Actually, we would have to say z. This whole thing right here could be symbolized z if you want. F subscript x means find the partial derivative of z with respect to x. So when we find the derivative of this, we're going to, because it says with respect to x, we're going to treat y as if it was a constant. So the derivative is 1/2 times 1. Copy what's inside there. Make the exponent -1/2. 1/2 minus 1 is -1/2. And then when we multiply by the derivative of what's inside, the parentheses, it's just 2x. The derivative of x squared is 2x. And the derivative of -y squared is going to be 0 because we're pretending the y is a constant. Simplifies to x over the square root of x squared minus y squared. Because this 2 up here cancels with that 2 down there. And we can make the exponent, we can make this negative exponent positive by putting x squared minus y squared to the 1/2 in the denominator. Number 8 also asks for the partial derivative of f with respect to y. So we go back to what the function is, the given function. When we differentiate with respect to y, the partial derivative with respect to y means pretend x is a constant. That makes the answer 1/2 times 1. Copy what's in the parentheses. Make the exponent -1/2. And now the derivative of what's inside here is 0 minus 2y. The derivative of what's in the parentheses is 0 minus 2y because we're pretending x is a constant when this y subscript is here. The partial derivative of f with respect to y is -y over the square root of x squared minus y squared. Because this negative is part of the answer. Here it is. 1/2 times 2 is 1. I could say 1/2 times -2 is -1. This y is part of the answer in that radical. Now we're still on number 8, where f of xy, f is a function of x and y. It's x squared minus y squared raised to the 1/2. It asks in the directions for the partial derivative of x at the point -2, 1. So we take our partial derivative with respect to x, which was right here, and we're going to just replace any x in here, where the red star is, with -2, and any y with 1. So using where the red star is, we're replacing x with this number, -2. Negative 2 squared is 4. There's a minus here by the red star. Y squared is 1. So we're going to take the answer as negative 2 over the square root of 3. And just leave it like that. Don't worry about rationalizing the denominator. And the last part of number 8 asks for the partial derivative with respect to y at the point negative 3, negative 2. Partial with respect to y is over here by the green star. That thing with the green next to the green star at this point is negative 2, which is just 2, over the square root of x squared, which this is x, so x squared is 9, minus, that's part of it. After the minus, we put y squared, which is 4, because this number is y. So the final answer there is 2 over radical 5. That's number 8. I'm going to do one more from this section. Number 42. The Cobb-Douglas model. Riverside Appliances has the following production function for a certain product. I won't write what it is. Where P is the number of units produced when X units of labor and Y units with X units of labor and Y units of capital. Part A in this exercise is to find the number of units produced with 2,500 units of labor and 1,700 units of cost. Actually, I will write this down. So the production function, P is the number of units produced, where X is the units of labor, Y is units of capital. The number of units produced is 1,800 times X raised to the 0.621 times Y raised to the 0.379. So part A is asking for the number of units produced, P for produced, with 2,500 units of labor and 1,700 units of capital. That's just telling us replace X with 2,500 and Y with 1,700. Replace X with 2,500. This 0.621 is the exponent. Replace Y with 1,700. There's Y, raised to the 0.379. Type all of this in the calculator, all this, and you get, make sure you do it on your own calculator, you get approximately 3,888,064 units produced. Part B, find the marginal productivities. That means marginal productivity means the productivity subscript X, and also after we find that, we're going to find productivity subscript Y. When I say subscript, I mean the partial derivative with respect to X. X is units of labor. So when we find the derivative of this function with the partial derivative with respect to X, that means the Y we're going to pretend is a constant. So if I rewrite this function, I'm going to switch the order. I can explain it better if I rewrite this as 1,800 times Y raised to the 0.379 times X raised to the 0.621. I'm writing it like this because over here, P subscript X means the derivative of this, I mean the partial derivative with respect to X, So we are supposed to pretend this is a constant because there's no x there. The derivative of this number inside the red times x raised to this number. We find the derivative by multiplying the exponent by the number in front. We're pretending all of this in the red is a number. When we multiply the exponent, 0.621, times this number in the red, we get 1117.8y to the 0.379. That's just the exponent times that number that's inside the red. We bring down the x, and we take 1 away from the exponent. 0.621 minus 1 is negative 0.379. And that's it. But there's other ways to write that. You can write it as 1117.8y to the 0.379. And this exponent is negative, so if we take that x to this exponent, the negative goes away because we're putting this in the denominator. And since the x and the y happen to have the same exponent here, this could also be written as 1117.8 times, in parentheses, y over x, that whole thing to the 0.379 exponent. So this here is called the marginal productivity with respect to x. But we're not done with part B because we also want the marginal productivity with respect to y. So now when we take the derivative of what p equals, we're going to pretend x is a constant. So before I do this, I'm going to rewrite the given. It's given that p equals 1800 x to the 0.621 times y to the 0.379. Partial derivative with respect to y means we're going to pretend this in the green is a constant. X is a constant. The derivative, pretending x is a constant, is the exponent up here, 0.379, times this number in the green, times y raised to this exponent minus 1. So multiplying the exponent by that number in the green, you should get 682.2 x to the 0.621. That number times that number is that number. Pretending x is a number. Bring down the y, and the new exponent, 0.379 minus 1, is negative 0.621. Since the exponent on the y is negative, we can rewrite this as 682.2 x to the 0.621 over y to the positive 0.621. And then these exponents happen to be the same. It might be a coincidence. So if you want to write it like this, 682.2, x and y have the same exponent, so we can put x over y in that order, x over y in parentheses, that whole thing raised to the 0.621. That's the marginal productivity with respect to y. And then 42 part C. Evaluate the marginal productivities at x equals 2500, y equals 1700. We take the marginal productivity with respect to x, and we're going to evaluate it when x is 2500 and y is 1700. So we have to go back and see what to plug that into. It's right down here, 1117.8 times the y over x that they're giving us raised to the 0.379. So it's 1117.8 times y over x. This is y over x. This is x raised to the 0.379. So put this calculation in your calculator and you should get about 966. The meaning of this is a small increase in labor. X is labor. So the meaning of this number, if cost is fixed, that's why we pretended the y was a constant when we did this, when we found the partial derivative. So if cost is fixed, not changing, constant. But when I say cost, I meant to say capital. Sorry. If capital is fixed, x and y are labor and capital. If capital is fixed, then marginal production, the P was production, being 966 means a small increase in labor, X was labor, will cause production to increase by about 966. Small or marginal increase in labor, that's what the X was, labor, will cause production to increase by about 966. Units. That's the meaning of the marginal production with respect to X, X being labor. So we pretended the capital was constant. Still on 42 part C, marginal production with respect to Y when X is 2,500 and Y is 1,700. So go back and find what that was. That's down there. 682.2 times X over Y raised to the 0.621. That was 682.2 times X over Y. That's X, 2,500, over Y, that's Y, raised to the 0.621. So get that number, comes out to be about 867. The meaning of this is, if since this is with respect to Y, the X was treated as a constant. So we'll say if labor is fixed, or constant, at that number 2,500, then a small increase in capital, a small increase in capital, because the Y here was capital, a small or marginal increase in capital will cause production, that's the P is production, to increase by about 867 units. So with the P subscript X, we kept the Y constant. Y is capital. This was the marginal production. P subscript y, we kept the x constant. X is labor. This 867 was the marginal production when the labor was kept constant. That's it. All right, the last section in this course is 6.3. And 6.3 involves using something called the D test. So I'm going to call this section the D test, even though it really is called something else. And somewhere on here I have the D test. I'm going to find it. Well, I don't know where it is. There it is. Okay, this is the D test. It is a test to find relative maximum and minimum values of a function when it's a function of x and y. So there's 4 steps here. You should write down all of these steps. You can copy them off of this. Pause the video and copy, or you can copy them from your textbook on page 566. Page 566. So here are the 4 steps called the D test. First thing we do is find all of these partial derivatives. F subscript x, and so on. This means the partial derivative with respect to x, the partial derivative with respect to y, this f subscript xx means the second partial derivative, first with respect to x and then with respect to x again. This f subscript yy means find the second partial derivative, first time with respect to x, first time with respect to y, and the second time again with respect to y. And this last thing is f subscript xy. We call that the second partial derivative. The first time we differentiate, it's with respect to x, and the second time it's with respect to y. So we find all of these partial derivatives. Then we set the first 2 equal to 0. The first 2 in this list, we set them both equal to 0 and solve the system of equations. That's an algebra problem. A comma B will be the solution to the system of equations. Then we calculate this value. It's called D. We take the third thing in this list up here, evaluate it at AB, times the fourth thing in this list, evaluated at AB, minus this last thing, evaluated at AB squared. If that number called D comes out to be greater than 0, then F has either a maximum or a minimum. If the thing we calculate called D comes out to be less than 0, a negative number, then F has neither a maximum nor a minimum at AB. And if it comes out to be 0 exactly, then we wasted our time. We cannot make a conclusion. If D is greater than 0 and F subscript XX, that's the third thing, evaluated at AB is negative, then we're going to say maximum at AB. If F subscript XX evaluated at AB comes out positive, then we're going to say F has a minimum at AB. So let's do page 571, exercise actually page 570, exercise 16. In this problem, a revenue function is given and a cost function is given. And I'm going to write down the profit. Profit will be a function of x and y is equal to revenue minus cost. So the profit, which is a function of x and y, is revenue. The revenue is given. It's 18x plus 25y minus 4x squared. Actually, sorry, this is not part of it. It's just 18x plus 25y. Then minus, here's a minus. I'm going to put the cost in parentheses. The cost is given. It's 4x squared minus 6xy plus 3y squared plus 20x plus 19y minus 12. Can I fit all of this? Barely. So revenue is given in the problem. Cost is all this. It's given. Revenue minus cost equals profit. So the problem says a concert promoter produces two kinds of souvenir shirt. One sells for $18 and the other for $125 or for $25. $18 and $25. So that's where the revenue came from. X shirts $18 a shirt, Y shirts at $25 a shirt. Actually, X and Y are in thousands. X 1,000 shirts, $18 a shirt. Y 1,000 shirts at $25 a shirt. The company determined that the cost in thousands of dollars for producing X 1,000 of the $18 shirts and Y 1,000 of the $25 shirts is this thing over here in the parentheses. The question is, how many of each type of shirt must be produced and sold in order to maximize profit? So first thing we're going to do is distribute this negative sign. The profit, which is a function of x and y, these are numbers of shirts, different kinds of shirts, is 18x plus 25y, distributing the minus 4x squared plus 6xy minus 3y squared minus 20x minus 19y and plus 12. There's a few like terms, so p of xy after combining like terms is negative 2x plus 6xy minus 4x squared plus 6xy minus 3y squared plus 12. So we just combine the 18x and the negative 20x and the 25y and the minus 19y. I think all the rest of the terms just got brought down. I get a 4x squared plus 6xy minus 3y squared and plus 12. So to find the maximized profit, we're going to follow these steps right here. We're going to find 5 partial derivatives. Let's do that and then talk about what comes next. We find the p is the name of the function. The partial derivative with respect to x. P is used because it's the profit. So when we find the derivative of this with respect to x, we will pretend y is a constant. The derivative of negative 2x is negative 2. The derivative of 6y is 0 because we're pretending y is a constant. The derivative of negative 4x squared is negative 8x. 6xy Same as 6yx. The derivative is 6y because the derivative of a constant times x, like 6y times x, is the constant. And the derivative of negative 3y squared is 0. We're pretending y is a constant. The derivative of 12 is 0. So that's the partial derivative with respect to x. The partial derivative with respect to y, so now we pretend x is a constant. The derivative of this constant is 0. The derivative of 6y is 6. The derivative of this constant is 0. The derivative of 6xy is 6x. This is a constant times y. The derivative is the constant. The derivative of negative 3y squared is negative 6y. And the derivative of 12 is 0. So now we need the second partial derivative, xx. That means we go to the first time we took the derivative with respect to x, which was up here. And now the second time we differentiate, it's going to be with respect to x again. So we're looking at this answer where the arrow is and differentiating that with respect to x. And that makes the answer just negative 8. Because negative 2 is a constant. The derivative of negative 8 times x is negative 8. And the derivative of 6y is 0 because we're pretending y is a constant. Now we need p subscript yy. So the first y means look at this answer where the red arrow is and take the derivative of that. So that tells me where to look. This tells me to take the derivative of that with respect to y. Partial derivative with respect to y of this where the red arrow is going to be 0 plus 0 minus 6. The derivative of negative 6y is negative 6. Y is the derivative of 6x 0 because we're pretending x is a constant. All right, we need one more partial derivative. It's p subscript xy. The x being first means look at this where the green arrow is. Here, this. And then differentiate. So this tells me where to look. This says find the derivative of that with respect to y. I mean the partial derivative with respect to y. So we can, when we differentiate this, we're supposed to pretend x is a constant. The derivative of this constant is 0, the derivative of this constant is 0, and the derivative of 6y is 6. Now that we have all of these, we calculate d. This is called the d test, and d is equal to, well, we called the function f in the notes, but here we can call the function anything. We're going to call it p subscript xx evaluated. Oh, we can't use this yet. We have to first make a system of equations. So I'm getting ahead of myself here. Skip this. We have to set the first two derivatives that we found, the p subscript x and the p subscript y. We have to set both of those equal to 0. So the one in the green here, negative 2 minus 8x plus 6y, set it equal to 0. And the p subscript y also, 6 plus 6x minus 6y, we set that equal to 0 also. This is called a system of equations. One way to solve this system of equations is to add these columns. Just add all the way across. Negative 2 plus 6 is 4. Negative 8x plus 6x is negative 2x. This column adds up to 0. 6y and negative 6y is 0. This column, 0 plus 0 is 0. So we get negative 2x equals negative 4. We subtracted 4 from both sides. That makes x equal to 2. Then we plug this 2 into either one of these equations. Pick one or the other, doesn't matter. And plug in 2 for x. So I put the 2 in for this x, but you could use that one, either one. That's 12. 6 plus 12 is 18. So 18 minus 6y equals 0. Subtract 18 from both sides. So y equals 3. All right, now we use the D test. The formula for D is the function's subscript xx evaluated at AB. When I say AB, I mean the x and y that we just found here. That's the solution to that system of equations. Times P subscript yy evaluated at 2, 3 minus P subscript xy evaluated at 2, 3 squared. We're going to figure out this number. It's called D. So P subscript xx, somewhere around here. That's negative 8. This means it's negative 8 no matter what x and y are. So we really don't need the 2 and the 3 right now. P subscript xx is always negative 8. So that's negative 8. Evaluated at 2, 3, or anywhere. P subscript yy, looking for that. That's right here, negative 6. Once again, that's always negative 6. It doesn't matter what x and y are. That's negative 6. And then minus P subscript xy. That's over here. That also came out to be a constant, meaning it's always 6 no matter what x and y are. So that goes right there. Don't forget this exponent. That's part of the formula for what D equals. So D equals positive 48 minus 36, which is 12. So the important thing about this D is that it's greater than 0. The D we just found is greater than 0. So here's the thing. If D is greater than 0, then we have either a maximum or a minimum at 2, 3 in this case. So we have to look at this. P subscript xx. So D is greater than 0. The P subscript xx evaluated at AB, which in this case is 2, 3, is P subscript xx. That was this number, negative 8. It's always negative 8 at 2, 3, or any place. And because that's less than 0, here's the D test. Take a look. P subscript xx is less than 0 because it's negative 8. That means the function has a maximum at 2, 3. Maximum at 2, 3. When I say maximum at 2, 3, I'm talking about P. I'm talking about profit is maximum when x is this first number. And remember, x is in thousands of shirts. So we're going to say 2,000. X was the number of $18 shirts. 2,000 $18 shirts. And Y is the second number, 3. Y is also in thousands. Y was the number of the $25 shirts. That's it. Profit is maximum when X is 2,000. When 2,000 $18 shirts are produced and sold, and 3,000 $25 shirts are produced and sold. And the proof is right here. When the D is greater than 0, and P, the function subscript xx, is less than 0, that's when we have a maximum. If this number had come out positive, we would have said profit is minimum.